everyone, welcome back. I'm Domingos. I'm also known as DMA and appreciate when I'm called DMA. So today we have this limit to solve. We have a limit of a given function and having a, m, t, h and the positive real numbers. Okay, perfect. First approach that we know when we're solving limits, we always substitute the value of the variable to see if the result will be undefined or defined. Undefined, we have to solve. Then if it's defined, we don't need to because it's already a real number. So our value of x approximates to 0. So that means our value of x is 0. If we put 0 here, that will means we will have 1 over 0, which is infinity. And since those four are like positive real numbers, if we put m to the power 0, it's 1 because any number to the power 0, it's 1. And obviously, because of the condition as well, they are real positive numbers. So will be 1 here, 1 here, 1 here, 1 here. And then 1 plus 1 plus 1 plus 1 will be 4. 4 over this 4 will be 1. So the undefined form that we will get, it's 1 to the power infinity, so which is undefined. I'll just write like that. It's undefined. So since this limit will be undefined, that reminds us Euler limit. But first we have to consider that Euler limit has this characteristic. It's 1 plus x to the power 1 over x, which is the same as Euler. That is what we know and what we get. Okay, and for us to solve this limit, or when we usually solve this limit, we send the exponent at this side multiplying and we subtract minus 1. So that means we would say that this will be equal to Euler. Let me just carry on this side. I will just say this is equal to Euler limit when x times 0, when x approximates 0, 1 over x, which is the exponent comes here multiplying, 1 plus x, we subtract minus 1. It's done like this. If we check this one and this one cancel, x and x cancel, will become only Euler. So that's what we do always. We send the exponent here and we subtract minus 1. But the limit has to have the undefined form of 1 to the power infinity. Okay, so doing the same approach here, we know that 4 is outer exponent, it's outside. We don't need to worry about the 4 now. So doing the same principle that we just did here in our problem, then this 1 over x, which is our exponent, will come at the back. So the inner limit will be equal to Euler limit when x approximates 0, 1 over x times m to the power x plus ax plus tx plus hx over 4 minus 1. That's what we had here. And all this limit, it's to the power 4. That's what we have. This is 4 here. Okay, that's what we have in this limit. But now, what can we do? We can find the common denominator here. We have this expression minus 1. So this obviously we can cross multiply. This will become negative 4 and all this over 4. Now, since we have a minus 4 here, what we can do, we can split this minus 4 into minus 1, minus 1, minus 1. So if we do that, then we're going to have Euler to the power limit when x approximates 0, 1 over x. Then we're going to have m to the power x minus 1 plus a to the power x minus 1 plus t to the power x minus 1 plus h to the power x minus 1 all over 4. All this to the power 4. So minus 1, minus 1, minus 1, minus 1 goes back to minus 4. Now what happened? We have 1 over x multiplied is 4. We can change them. So I can put the 4 here because it's multiplication, so it's commutative. So we can change a times b, it's the same as b times a, so x times 4 is the same as 4 times x. So we can change. And now if we check this 1 over 4, it's a constant, can come outside of the limit. So this constant 1 over 4 can become here 1 over 4. It's not a problem. Now we have this limit. What do we do in terms of this limit? We're going to have now, that will be Euler to the power 1 over 4, limit when x approximates 0. we can split each one with its denominator. So we're going to have now in this case m to the power x minus 1 over x plus a to the power x minus 1 over x plus t to the power x minus 1 over x plus h to the power x minus 1 over x. Okay, all this to the power 4. Now if we check here, the limit of a lot of functions, adding each one of them, it's the same as you calculating each one with the limit. So the limit, the limit of the sum is equal to the sum of the limits. In other words, that's what I'm saying. So that means we have the limit of this expression plus the limit of this expression plus the limit of this expression plus the limit of this expression when x approaches 0. So this is a fundamental rule of a limit. So we know already that limit of t when t approaches 0 of t to the power x minus 1 over x is equal to ln of the base t. Okay, so since this limit is similar to those ones, so we can apply the same approach. So we have m to the power x minus 1 over x. Since x approaches 0, so that means this will result in ln of the base m. So that means we're going to have Euler to the power 1 over 4 ln of m plus ln a plus ln t plus ln h, all that to the power 4. Now we know in log, when one or more log are adding one another, then we keep the log of course, we multiply the arguments. So that means what we're going to have is Euler to the power 1 over 4 ln of m a t h, all to the power 4. But since this 1 over 4 is multiplying the log, we can send as the exponent of the argument of the log. So this can become here 1 over 4. Let me just erase this side. So 1 over 4 all to the power 4. Now, what is ln? Ln, we know that it's log of that expression of the argument to the base Euler. So we have base Euler, we have base Euler. We can cancel out when the main base of the exponent of the power is the same as the log base, which is Euler. So we will remind with the argument, which is math to the power 4, 1 over 4 I mean, times 4. So 4 and 4 cancel out, then the result will simply be maths. Okay. So if you enjoy, leave your like, your comment, subscribe, and most importantly, share with your friends.